The universe is held together by four fundamental forces, one of which is mostly ignored in your standard high school physics class. This force is responsible for many of the phenomena in the universe, but also impacts our day-to-day lives here on planet Earth. From carbon dating old fossils and relics to being the driving force that allows for nuclear fusion that powers all the suns in the galaxy, this force is greatly overlooked and underappreciated. High school physics teaches us that the universe is governed by four ruling forces: the gravitational force, responsible for keeping planets in orbit as well as keeping us on Earth; the strong force, which acts inside the tiny nucleus of an atom to hold together protons and neutrons; the electromagnetic force, that allows for the attraction and repulsion between opposing and similarly charged particles; and finally, there is the weak force, the nature of which we will be discussing in the next few minutes. First of all, it is important to understand the basic background of particle physics in order to grasp the concept of this fundamental force. Everything in the universe is made up of atoms, and atoms are made up of three types of subparticles: protons, neutrons, and electrons. While the protons and neutrons are found in the nucleus of atoms, the electrons orbit around the nucleus in clouds called orbitals. Now, protons and neutrons are made up of quarks. While protons are made up of two up quarks and a down quark with charges of positive 2/3 and negative 1/3 respectively, neutrons are made up of two down quarks and one up quark. There are also four other types or flavors of quarks: charm, strange, top, and bottom. Electrons, on the other hand, are a type of lepton. There are five other types of leptons, from the more familiar neutrino to the less known tau and muon. Neutrinos contain positively charged bosons, whereas electrons do not. The weak force in general will be interacting mostly with leptons and quarks through bosons. Getting back on track, the weak force is named as such because its range of action is limited to approximately 10 to the negative 17 meters. That's 100 times smaller than the distance between protons and neutrons in the nucleus of an atom, which tends to measure around 10 to the negative 15. At this point, you may be wondering, why does such a small and seemingly irrelevant force impact me, and why should I care about its effects? And to that I say, let's start with the first example of weak forces in nature. The sun, the driving source of energy, heat, and light in our solar system, could not produce that energy if not for the weak forces. If we look on the inside of any new star, we will find hydrogen atoms, packed together and being forced closer and closer due to the large mass of the star. When the mass of the star gets large enough, those hydrogen atoms begin to fuse together to form helium. This is a process called nuclear fusion, and it is found at the core of every star in the universe. As stars increase in mass, the star will be able to form heavier and heavier elements by fusing together larger and larger nuclei. But for the time being, we'll focus on the hydrogen to helium reaction. This is also known as the proton-proton chain, and the weak force allows for the unstable helium-2, that is produced from this reaction, to be converted to the more stable helium-4 through beta decay. This allows for the nuclei to fuse and create energy and light. Without this crucial nuclear interaction, plants wouldn't grow and people wouldn't get sunburns if they stayed in the sun too long. Now, as it was mentioned, the weak force is responsible for the beta decay found in nuclear fusion. But what does this process entail exactly? Well, beta decay in the context of nuclear fusion is generally described as the process of changing a neutron into a proton and electron. If you remember from the beginning of this video, a neutron has two down quarks and an up quark, whereas a proton has two up quarks and a down quark. This means that in the beta decay process, something must be interacting with the quarks that has the ability to change their flavor. This is where the weak force comes into play. First of all, it is important to note that the carriers of the weak force are W and Z bosons, so one must be present in order for this reaction to occur. In this case, we have a neutrino present. The first thing that occurs is the neutrino releases a positive W boson, and it itself becomes a negative electron. Then that boson moves towards the nucleus and into a neutron, where it is able to interact with one of the down quarks in the neutron and change its flavor into that of an up quark with a positive charge. After this process has finished, we are now left with a new proton and an electron. It is important to note, however, that while we may be only talking about beta negative decay in this video, weak forces play the same role in beta positive decay, which changes a proton to a neutron. Weak forces explain many aspects of life that we all take for granted, from the nuclear fusion that fuels the sun to the carbon dating of ancient relics. Because we know that isotopic abundance of an atom will stay relatively the same at any given time, scientists can calculate the value of the ratio between carbon-12 and its heavier and less stable isotope, carbon-14. Because carbon-14 is unstable, over time it will undergo beta decay, where a neutron is converted into a proton, and it will become nitrogen-14. Because carbon-14 decays at a constant rate, scientists can look at the amount of carbon-14 that has not decayed and compare it to the carbon-12 in any given artifact. This allows us to know how old Egyptian mummies and Greek art really is to a fairly specific degree. Now that we've discussed the examples of weak force interactions in nature, as well as how it works, it's time to explain why it is the least understood and most confusing force in physics of the four fundamental forces. A major component to physics experiments and thought processes is the concept of symmetries, meaning the things you can change in the experiment without changing the outcome. The first symmetry we will be talking about is p-symmetry, or parity symmetry, and it is the idea that the outcome of an experiment should not change depending on where the observer is watching it from, top or bottom, forwards or backwards, or left and right. And this symmetry remains true for the electromagnetic force, gravity, and the strong force. However, it fails to remain true for the weak force. You see, particles have a property called spin, and what should occur if p-symmetry was true would be if something with spin decays, particles should fly out in a random direction. However, after an experiment was done using cobalt spinning, scientists found that the direction or spin of the resulting decay particles actually depended on whether the cobalt was spun clockwise or counterclockwise. This is because to the weak force, spin really does matter. The weak force will only act on clockwise spinning matter particles and counterclockwise spinning antimatter particles, which also makes it the only force to treat matter and antimatter differently. But this is not the only symmetry that the weak force violates. Physicists also thought that an experiment should work the same regardless of the direction time is moving. And it does, at least for gravity, electromagnetic, and strong forces. However, the weak force does not, due to particles called B0 mesons. There are regular B0 mesons, and then there are anti-B0 mesons, and the weak force can switch freely between both of them. However, for some reason, it takes a longer amount of time for the weak force to make a B0 meson into an anti-B0 meson than the other way around. This makes it the only force we've seen so far to violate time symmetry as well. The weak force is weird and has been confusing physicists for centuries, which is why it is likely not taught in high school. However, I hope this video has taught you a little bit more about the importance of the weak force as a fundamental force in physics, and maybe gives you something to think about next time you're sitting in the sun soaking up all those rays that wouldn't exist if not for the weak force.